Good afternoon, everyone, and happy International Women's Day. Today, we're going to continue our discussions on mean curvature flow. So recall we're interested in getting a good handle on what happens at singularities, finite time singularities of the mean curvature flow, with a view to eventually doing some surgery. Now, we've had a couple of weeks break, but we're pleased to have Devesh back with us, who's going to continue speaking to us about asymptotic convexity in mean curvature flow. Thank you, Devesh.
Thanks, Tim. So we'll begin where we left off. And I'll do a brief review of the previous talk. So we were exploring convexity in mean curvature flow and got the idea that we can explore this using elementary symmetric polynomials. And we were trying to prove a certain convexity estimate, which goes as follows. So if we have a smooth solution of the mean curvature flow, where the initial hypersurface is compact and of positive mean curvature, then for any eta positive, there exists a constant depending only on our initial conditions and n, so that sk is greater than equal to negative eta times h raised to k minus c. So sk, the negative part of sk can be controlled in some fashion up to a constant, and with a factor eta, which is arbitrary. And we saw that heuristically this will imply a convexity limiting, convex limiting hypersurface, and we'll come to that later rigorously in this talk. And so we'll restrict our attention to the case k equals to 2. The higher estimates can be done similarly using a different function. And the function we got was this function, that mod a square upon h square minus 1 plus eta multiplied by h raised to sigma. And we saw that if we have a uniform bound on this function, then it implies the convexity results we are hoping for. So we tried applying maximum principles and calculated its time derivative, which was all good except one bad term. So you have Laplacian here, some inner product gradient terms, another gradient term, a difference term, plus sigma times mod a square g's. So this is a bad term, and we can't directly apply maximum principle. However, for sigma equals to 0, we got a nice result that in mean convex setting, mod a square upon h square is less than equals to certain constant, depending only on the initial hypersurface. And also by algebraically, h square is less than equals to n mod a square. So for mean convex hypersurfaces, the blow-up rate of a second fundamental form and mean curvature is the same. And we'll use this quite often. This also implies a bound on G. So G is less than equals to certain constant time h raised to sigma. We'll denote this constant same. And so because we can't directly apply maximum principle on G, we hope to get an LP estimate. And to do that, we get to the integrals of g raised to p. So the time derivative of g raised to p satisfies a certain inequality. However, the bad term manifested here as well. But one thing to notice is that all the good terms are gradient terms. So this is gradient g square, this is gradient h square, this also contains gradient. And so in this talk, I'll estimate this bad term as this and get a bound on this bad term in terms of the rest of the terms. So this was done in last talk. And now we come to this part, that this bad term can be controlled up to certain factors times the good terms. And like I mentioned, all the good terms contains gradients, And the good term is a purely curvature quantity, mod a square, without any derivatives. So to do this, it's only a sketch. We calculate the Laplacian of G, which is some big quantity. And notice that we have an identity relating gradients to a purely curvature term, which is the Simon's identity. It says that Laplacian of mod a square is equal to twice this inner product, Hij are the components of second fundamental form, times gradient I, gradient J of mean curvature, plus twice Laplace gradient A square plus 2z, where z is some difference of principal curvature, some algebraic identity of principal curvatures without any gradient term. So we substitute the Simon's identity at this place, and then multiply our equation by a certain factor to remove h raised to sigma there. So there was some h raised to sigma appearing here. We multiply to eliminate that term, and after some calculations, we'll get that this g multiplied by z upon h square can be expressed in terms of other terms. And like I said, also I have applied the divergence theorem on this Laplacian. So we are getting only this gradient quantities. So yeah, again, one point to notice, this is purely curvature term. These are all gradient terms, however, gradient, gradient, gradient. Oh, yeah. And so this gives us a hope that we can control the back term, possibly in terms of other gradient terms. And we also have a bound on z in terms of h square and mod a square. And utilizing the fact that in mean convex setting, g is also less than equals to certain factor, certain constant time h raised to sigma. So yeah, we do some elementary estimates on the rest of the quantities and club them together to get this. So we get some purely we simplify our expression a little bit using some estimates. And now for this cross term, we use AMGM inequality to get some factors involved in, expressed in terms of Nabla G and Nabla H. So this cross product can be written as less than equal to some factors times squares. And substituting this back, and you'll get the required estimate, which was this, that the good term can be calculated up to certain factors. The bad term can be calculated up to certain factors times the good terms. Here, P was the LP and beta is arbitrary. P is required to be greater than 2 for this to hold. So we've gotten some hold over the bad term, and in fact, this will imply that the LP norm of G sigma comma eta is non-decreasing function of T if the following holds. So if our P is large enough and our sigma is sufficiently small, which sigma is sufficiently small, specifically in the order of P raised to negative half. I did not go over too much details, but roughly the idea was that. So now we come to the next part, which is getting an L infinity estimate out of these LP estimates. And this is where the Stampacchia iteration comes in. We use the following. Before that, I state the Stampacchia lemma, which states that if I have a non-negative, non-increasing function satisfying a certain bound, so assume that my h, the function starts from k naught to infinity, and I have two variables, h greater than k, or both greater than k naught. Then psi of h less than equal to certain factors times the difference to the power alpha times the small psi of k raised to beta, where beta needs to be greater than 1. And this is some decay condition on a decreasing function. And this is strong enough to say that after a certain point, the function will become 0 and it will remain 0 after that. There's a way to calculate the constant as well. So psi k naught plus d is 0, and the function was non-increasing, so it will remain 0 after that. And we want to apply this Stampacchia lemma to prove a uniform estimate on our previous function, and we'll use the LP estimates we have acquired so far. So the next part will get technical, but feel free to ask me, feel free to interrupt me anytime. So now I begin the proof. So we want to prove a uniform estimate of G using Stampacchia. So before that, choose a K naught such that K naught is the supremum of G over the initial manifold with sigma varying over 0, 1. This is a compact setting, so supremum is not infinity. And I define a certain function as the difference G sigma comma eta minus k, the positive part of it, raised to p by 2. And ak is the domain where this function is positive. So this function is positive where g is greater than k. And also, if v square is g sigma comma eta minus k raised to p, which has sufficient derivatives for large enough p, we can differentiate this function. And so we want to apply Stampacchia lemma to this integral, which measures the area of AKT up and integrated over the time our solution survives. So, and we'll see that if we are able to prove that this function is 0, it will imply a uniform bound on G, because then AK will be empty sets, and so G needs to be less than equals to K over all time. Okay, so I'll begin. The proof is divided over 3 steps. Differentiating v square with respect to time. This was differentiation of g raised to p, integral of g raised to p. This we have obtained before, but we'll just I'm using v square now. And so certain time derivative of our integral plus nabla v square is less than equals to sigma p times mod a square v square. This is this can be manipulated from the, so d by dt of g times some, this will be our nabla v, and I've absorbed this, eliminated the p factors, less than equals to this term, the bad term. So this term goes over here, and these are all negative terms, so we can ignore them. Less than equals to p times sigma times the bad term. In the notation of v now, v was g sigma, v square was g sigma eta minus k raised to p. Now I'm using that v square is less than equals to g, because it was some difference. V was g minus k, the positive part of that. So v square will still be less than equals to g raised to p. And our second fundamental form is also some factor times, is less than equal to some factor, some constant times h square. We have another result from Michael Simon that we have a bound on LQ norm of functions in terms of a constant times this gradient terms, and another factor which involves an integral of mean curvature, where Q is certain number based on the dimension we are considering. So, and we'll use this term, we'll use this inequality to get rid of the gradient term here. So before that, I can estimate this factor. I'll show how. So we can estimate the Hn factor in the integral using the previous proposition and equality. So firstly, notice that if I have h raised to n multiplied by some g, and our g was this difference times h raised to p sigma, h raised to sigma, which with the power of p here. So we can absorb Hn to this part and just say that this is the integral of g sigma prime, where sigma prime was sigma plus n by p. I have absorbed this n to this p sigma and divided by p. So this integral is also an integral of type g raised to p with a different sigma. And so if we let p large enough and sigma small enough, again, then sigma prime is also small enough in. So this is also non-decreasing, and provided our p and p is large enough, sigma small enough, both can be managed. I'm not going over the details right now, but it can be done. So this function is also non-decreasing over time. Sorry, non-increasing. And yeah, so that factor was integral of h raised to n raised to 2 by n over AKT. AKT was a domain where our V was positive, or that. So this is also less than equals to a integral over AKT G by K raised to P, and G is greater than K over this domain. So this this quantity is greater than 1, and this inequality is true. Now I'll bring the K out and absorb my H to get a different G with a different sigma. The integral over AKT is less than the integral over MT. And if we again let our P large enough, sigma small enough, this integral is decreasing over time. So less than equals to the integral over M naught. And we chose our K naught such that K naught was the supremum of this function with variations over sigma. So for even sigma prime, we can have a bound on this. So this is less than equals to volume of M naught times K naught, K naught divided by K. K was coming from this part, raised to power 2p by n. So we have got hold of one term in the Michael-Simon-Sobolev type inequality, and we'll use that to our advantage. So we can now K is still a variable here, and we can choose that this quantity is small enough. In particular, I'll fix a K1 again greater than K naught, so that this quantity is less than equals to 1 by 2 Cn. So going back to Michael-Simon result, I am choosing that this quantity is less than equals to half this complete quantity. And this can be done provided your P is large enough, sigma small enough. And so if this is less than half, this is half, and I'll bring this factor over here. So to get okay, so I can choose my case as that this is less than half. I'll bring this quantity over here, and find the inequality where LQ norm of V or V square is less than equal to certain number times the gradient. And I can eliminate gradient using, I can substitute this result here. So we have eliminated the gradient term in terms of the time derivative of V square and the LQ norm of V square, which is less than equals to certain constant times h square g raised to and g sigma comma eta raised to p. Any questions so far? Okay, I'll resume. So now that T naught be the time where the supremum is attained of the integral over V square, and we have a way to handle if the supremum is not attained in the interior as well. First, let T naught be the interior for now. So integral of this, we'll integrate this inequality up to T naught to get some, we are throwing away the initial term, which will be negative. So integral of V square of n at mt naught plus some factor times integral from 0 to T naught less than equal to again some factor times integral from 0 to T naught. And we integrate this now again from T naught to capital T minus small minus epsilon for epsilon small enough. So we get an integral like integral at m capital T minus epsilon V square minus integral m T naught plus certain integrals from T naught to T minus epsilon, T naught to T minus epsilon. We can throw away this term. So we can throw away this term and add half of this to eliminate to get our integrals from 0 to T naught to T minus epsilon. So we'll get that half of integral mt naught V square plus 1 by 4 cn, since we multiplied this by half. So this half comes over here and 1 minus half 1 by 4 cn times integral from 0 to T minus epsilon, the LQ norm of V square less than equals to certain constant times 0 to T minus epsilon integral over AKT. And now this can be written as supremum. The T naught was the point where this function was achieving supremum plus some integral from 0 to T, epsilon approaching 0, we are taking the limit here. So 0 to capital T integral less than equals to, I'm managing the constants so that this becomes 1, less than equals to certain factor times integral from 0 to T of this quantity AKT h square g sigma theta raised to P. And so this finishes step 1. Again, if you have any question, feel free to interrupt me. We move on to next step, and we use the Minkowski inequalities now, that or holder that interpolation inequality for LP spaces. It says that a Q naught norm of F can be bounded by some multiplication of Q and R norms, where you have some holder type condition. 1 by Q naught is alpha by Q plus 1 minus alpha by Q, satisfying certain things. We chose we choose R equals to 1, and like for certain numbers here satisfying this holder conditions, we get that the Q naught norm, LQ naught norm of V square can be bounded in terms of LQ norm and L1 norm, with certain exponents, 1 by q naught times q, 1 minus 1 by q naught. And using this, we integrate this in time and use Young's inequality. So we integrate, we first take the exponent q naught both sides, and then integrate over time, take back the exponent 1 by q naught. So this is, I'm using this is less than equals to supremum. The supremum comes here. This factor of this, the time integral goes there. Yes, so q naught norm of this integral is E bounded by some supremum of the quantity we are considering, b square over akt, with some exponents decided by interpolation inequality. And now this, I'm using Young's inequality here. So this factor times some power, this factor times some power is less than or equals to supremum divided by q naught minus 1. This is inverse of this times this factor q naught. And this can be written as less or q naught greater than 1. This is less than or equals to the just pure sum of these two terms. And this was the result of step 1, that supremum of v square plus 0 to t integration of this LQ norm of v square is less than or equals to certain factors times this integral h square times g raised to t with sigma and eta. We have chose some constants. And now we can start the Sampakya lemma, the getting the appropriate bounds to apply Sampakya lemma. Let psi k be the area function I mentioned earlier. So this measures the area of the domain where our v square is positive, which is same as saying that g is greater than k. Psi k measures this integral over the time our solution to MCF exists. We will obtain bounds on psi along with which we'll obtain bounds along with which we can apply Sampakya lemma, and which will further imply a uniform bound on G. We apply Holder lemma again to this inequality, 0 to capital T integral of akt v square is less than or equals to, now the Holder is over v square and 1. So these are Holder conjugates, 1 by q naught, 1 minus 1 by q naught, and multiplication of this is v. And I get my volume or area function here. This was the psi k we defined previously. So this is less than or equals to psi k raised to power 1 minus 1 by q naught, some factors. And this was, so step 2 concluded with LQ naught norm on v square, which is what I'm getting here. So the LQ naught norm is again less than or equals to, can be bounded in terms of this multiplication h square and g. And I'm also getting my area function here. We'll apply Holder inequality again, but with some different weights. Let R be greater than 1, which will be chosen later, and applying Holder again on this term now. So you see, there's some multiplicative identity will appear later. That applying Holder again on the right hand side with weights R and R minus R, the conjugate of R, I get that this factor is less than or equals to the area function times this function raised to power R. And we get our area function again with a different exponent this time, 1 minus 1 by R, which we can manipulate later. And again, for R large enough, I can absorb the H2R this time to get a different sigma double prime, which is sigma plus 2 by P. For R large enough and P large enough, sigma small enough, there exists a certain constant such that this again becomes an integral of function like G with a different sigma, which has a bound based on the LP estimates we did so far. And so for, again, R large enough, this becomes a decreasing function, which can be bounded. I am denoting that bound by C9 here. C9 raised to 1 by R we are getting. So H square is less than equals to the area function and raised to 1 minus 1 by R multiplied by some constant. And now we get to the part where we can apply Sampakya. So the difference H, so let H be greater than K, greater than equal to K1. This difference raised to P times psi h was the area over H. This is less than equals to the V square, since V square was G minus K, and since we are integrating over AH, it's the domain where G is greater than H. So we can apply this inequality. And AH is smaller than AK. There should be one more intermediate step where I'm doing this over AH. And then AH will be less than equals to AK because H is greater than K. So again, so AHT was the domain where G is greater than H. So I can use this inequality. And now I have bounds on the integral over V square over AKT, which was the result we obtained. So using Holder type inequalities, the integral over V square over AKT was less than equals to the area function times, again, some constant times area function with some certain exponents. I'm combining these two results here. So this H square is also bounded here. So V square is bounded in terms of the area function times certain constant raised to a different exponent this time. I'm summing over the two exponents, 2 minus 1 by R minus 1 by Q naught. And this indicates that we are getting some progress and we can apply Sampakya now. And for R large enough, this constant can be made greater than 1 so that 2 is sufficient. And 2 minus 1 by R is small enough. 1 by R is small enough so that this quantity remains greater than 1. And we fix an R greater than Q by Q naught minus 1, which makes the previous exponent greater than 1. P large enough, sigma small enough so that sigma P here, sigma so that sigma P is still less than 1. And this gives that psi of H is less than equal to certain constant time H divided by H minus K raised to P multiplied by H raised to K times exponent gamma. So we are in the domain of Sampakya lemma now. And this inequality implies that this decreasing function is 0 after a certain point. So this psi k is 0 after k 1 plus d. D can be figured out, but that's not the important part. This function is 0. So the area function of this area function is 0, which implies that my G is less than equals to K for all time t, where the solution is considered. So G is less than equals to certain constant. And again, that G was equal to mod A square minus 1 plus eta H square less than equals to K H raised to 2 minus sigma. And we saw that this estimate this estimate implied the convexity estimates we were hoping for. We can trade h raised to 2 minus sigma for a constant with this. So h raised to 2 minus sigma is less than equals to 2 gets here, provided we supply a constant. This was equals to minus 2s2. And so minus 2s2 is less than equals to twice eta times h squared plus 2 some constant. So we flip the inequality by multiplying -1 both sides, and we get the S2 estimate. Now, so far we have only obtained S2 estimates, but this can be done choosing a different function or an induction type argument. You build up from 2 and go to n, or we chose a different, more clever function for different case, like we chose for S2. G was the G we chose for k equals to 2. This finishes Stampacchia iteration, and we get a uniform bound out of the LP estimates. Now, I'll come to the other part, and how does this imply, and what do I mean by asymptotic convexity coming from this? Before that, I will go on to classify singularities of MCF. The equations of MCF can be used to get an evolution equation of norm of second fundamental form. So norm of second fundamental form satisfies the evolution equation where the norm square time derivative of this is equal to Laplacian minus twice gradient square plus 2 raised to plus 2 times norm to the power 4. This is, I can ignore this negative term, the plus should not be there. And if we consider the time when mod a square achieves the maximum, this equation we can derive a bound on the norm at time t using some maximum principal methods. So this norm is greater than or equals to 1 by 2, the time difference from the maximum into the maximal time. And if there exists a constant c greater than 1, so that this can be bounded from above by quantity of this time. I'm taking a square root here. So c times c divided by square root 2 times capital T minus small t. We say our flow is developing a type 1 singularity. So it's bounded on from the below by 1 and from the above by c. If such a constant does not exist, we say our flow is developing a type 2 singularity. In this case, the limb sup of maximum of mod a times square root capital T minus small t goes to infinity, since there does not exist such in C. Now, type 1 singularities are somewhat better understood, and in fact, there's another result called monotonicity formula, which will imply that a limit of type 1 singularity satisfies certain equation. So H can be given in terms of is the inner product of X, where X was the parameterized function for our hypersurface, no inner product with the normal. And in fact, Huiskin classified compact hypersurfaces. So he stated a theorem that if Mn is with n greater than or equal to 2 is compact, non-negative mean curvature, and satisfies this equation, then M is actually a sphere of radius square root n. This is only for compact though. We don't know. There's some different result for non-compact. And now we move on to type 2 singularities. So a type 2 shows a maximal solution which develops a type 2 singularity. On it, we choose some sequence in space-time such that we are picking points in m and times such that this h square times difference term t minus tm achieves the supremum here. So this is h square x comma t multiplied by some time difference term with a negative t. So t minus 1 by m minus capital T. We are taking supremum over compact set. So the supremum is achieved. So this also, as m goes to infinity, this sequence approaches the maximal time. So before the singularity is approaching, we are taking some space-time points where this fact h square multiplied by time difference t minus small t, the supremum is achieved. And for now, label some points. So Lm is the point. Lm is the mean curvature of this space-time point. Alpha m is negative of mean curvature square multiplied by Tm. Omega m is the mean curvature square times the time difference t minus 1 by m minus Tm. And the conditions of type 2 singularity implies the following holds. So as our sequences are approaching capital T, the maximal time interval, mean curvature blows up. We are choosing some certain supremums, even though we have multiplied by time difference, and it will still go to infinity. This is less than a constant. This is less than capital T. So Lm will still blow up. Alpha m is the time. Alpha m will also blow up. It's less minus Lm square Tm. Tm is bounded. So alpha m blows up to negative infinity. And the type 2 condition comes here. Omega m goes to infinity. This mean curvature square times time difference term goes to infinity. This was the condition for type 2 singularities. So as we chose the points in space-time, we have some results that mean curvature blows up, alpha m blows up to negative infinity, and omega m also blows up. Now, using these space-time points, we rescale our hypersurfaces. We rescale the hypersurfaces to analyze the limiting behavior. And I'm doing three things here. One, space translation. So I'm shifting the points such that xk at 0 is origin. So this is done by taking a negative of x at xm comma tm. This is just a space translation. Then I'm also doing a time translation such that this happens at time t equals to 0. And I'm also doing a parabolic rescaling. So parabolic rescaling can be done on MCF and it will still be a solution. So I'm multiplying t by Lm raised to negative 2 and the space part by Lm. This will again be a solution of MCF. But we have some other with extra conditions that at time t equals to 0, at xk, the parameterized hypersurface is actually at origin, and the mean curvature at this space-time point is also 1. So you can think of this as I'm choosing a sequence where my mean curvature was blowing up, and I'm looking at it under some magnifying glass of different powers for different points, space-time points, and I'm also slowing down time to analyze the behavior. So we get a better idea of what's happening in the singularity. And from the supremum conditions, we get that these rescaled hypersurfaces have mean curvature bounded. So hm square x comma t, if I multiply my parameterized hypersurfaces by Lm, h becomes h needs to be multiplied by 1 by Lm. It's the inverse relation, like a sphere of radius r has mean curvature n by r. So from the supremum points we consider, this is bounded by capital T minus 1 by m minus Tm divided by T minus 1 by m, this quantity. I'm getting this from this part. So for any arbitrary point, h square of some arbitrary space-time points times T minus 1 by m minus T is less than or equals to hm of that point. So this was my Lm. I'm dividing this over here. So h square by Lm square is less than or equals to this Tm, the time difference factor for Tm, divided by this time difference factor. So this quantity is less than or equals to, this was my m comma Tm. So I'm dividing h square here to get some inequality based on the time differences. T minus 1 by m minus Tm divided by T minus 1 by m minus Tm minus Lm raised, this was coming because of here. And this evaluates out to omega m divided by omega m minus T. Now, because of the type 2 conditions we considered, omega m was blowing up. So from the previous lemma, omega m was blowing up, and for m not large enough, I can consider my omega m large enough so that the mean curvature in now these subsequence of in this sequence of hypersurfaces is bounded. And so the maximum of h is less than or equals to 1 plus epsilon for all m greater than or equal to m naught. That one thing I forgot. So because of the time scaling, we also get a shift in our maximum solution for this sequence of hypersurfaces, and the time for which they exist is alpha m, from alpha m to omega m. And this can be done by, so this needs to be greater than or equal to 0, and so T will be greater than or equals to Lm square times Tm negative of that, which was my alpha m. And again, so this needs, and if you consider this inequality with Lm raised to negative 2 T plus Tm less than or equal to capital T, you'll get omega m. So the time for which these sequence of hypersurfaces exist is parameterized by alpha m to omega m. And because of the type 2 conditions, our h was bounded. H can be bounded if for high enough index. This curvature bound will also imply this bound on mean curvature will also imply bounds on second fundamental form as well as covariant derivatives. And further observe this, the Kate symmetric polynomial of principal curvature also gets rescaled. In particular, it gets rescaled by the same factor, mean curvature gets rescaled, so Lm raised to minus k. Now, from the previous results, this was greater than or equals to negative eta times h raised to k negative c. So I'm multiplying L raised to minus k over the inequality, the previous convexity results. This Lk will be absorbed here to get the new mean curvature for this parameterized hypersurface, this hypersurface indexed by m, and this factor will remain there. And in my new rescale hypersurface, h was bounded. So h can be bounded by 1 plus epsilon here. In particular, this will imply that the sk goes to 0. This factor blows up, and so this quantity goes to 0. My eta was arbitrary. Epsilon can be made as small as I would like, which implies that sk goes to 0. So if I invoke Arzela-Ascoli theorem, there exists a subsequence of xm converging uniformly on compact sets of Rn plus 1 times R. This is the space factor, this is the time factor. It converges to a limiting solution. And further, this proves the asymptotic convexity of the flow in the following sense. So summarizing all the results, if I have a maximal solution of the mean curvature flow with initial hypersurface compact and of positive mean curvature, assuming that the flow develops a type 2 singularity, I can choose a rescaled flow. I can choose space-time points and some rescaling at particular times, a rescaled flow which converges smoothly on every compact set to a limiting solution, which I'll denote by x infinity, which is defined for all time. This is an eternal solution. So the time for which it was defined was alpha m to omega m. Omega m was blowing up because of type 2 conditions. Alpha m blows up because h blows up. So my limiting solution of mean curvature flow is actually eternal. Further, it is convex because of the SK inequalities we got so far. And in the limit, the mean curvature is satisfies certain bound, which is that it's greater than 0, less than equals to 1. And further, the equality 1 is also achieved at the origin. This is how we chose our space-time points, so that HM is equals to 1. So summarizing all this, we get an asymptotic convexity of type 2 singularities of mean curvature flow. Yeah, this concludes the talk.
Thanks very much, Devesh, for taking us through all of these details. Does anyone have anything they'd like to say to Devesh or ask him about the talk?
I have one question. Does the convexity estimate that you proved at the end of your Stamp-Kia iteration, does that imply that even without rescaling, the lowest eigenvalue, the lowest principal curvature is bounded below?
I don't know.
Okay, no worries.
No, I need to think. I don't know.
Yes, because I couldn't think of any like counterexamples to that. So
okay.
Yeah, I think it does imply that, because if your principal curvature wasn't down below, then mod A squared would be blowing up, mean curvature would be blowing up. And then your estimates would apply and give you a lower bound, right? So they get a contradiction if the kappa i's go to minus infinity. Yeah, so I think you do get that.
okay, thanks.
Any further discussion questions? All right, then let's thank our speaker again for his 2 talks thus far.
Thanks, Devesh.
Cool. Thank you very much, Devesh.
Thanks.
Yeah, stop sharing.
Cool. The plan is actually to continue next Friday. The plan so far is to not have a break. Our next speaker, Tenkai from MIT, has agreed to speak to us. I will point out, though, that given we've got an international speaker from America, we're going to have to concede our late time. We're going to have to push this a bit earlier. He asked me what the earliest we could do is, and I said 10 a.m. I wasn't willing to bet that everyone would be willing to do 9 a.m. So I said 10 a.m. and he was happy with that. So at the moment, the plan is 10 a.m. next Friday. Hopefully we'll see you there. Thanks, everyone. I'll stop the recording now.